Mrs. Often, and in this video we'll be discussing solving logarithmic and exponential equations, including both those equations that need to be solved using logarithms and those that can be solved with the one-to-one property, either with the same base logarithm or the common base of exponents. Let's get started. At the end of this video, you will be able to solve exponential equations using a variety of methods, including solving exponential equations in quadratic forms, and you'll also be able to solve logarithmic equations using the one-to-one property and exponential and logarithmic equations using the definition of logarithms. To begin with, let's review solving exponential equations that have the same base. For example, you could have the equation 2 to the 3x minus 8 is equal to 16. You'll notice that 2 and 16 both can be written as exponential equations or exponential expressions with the base of 2. 16th being 2 to the 4th. Therefore, we can write the equation 3 to the x minus 8 is equal to 4. And because 3x minus 8 is equal to 4, we can solve this just like any other algebraic equation that's a linear function. And we receive the answer x is equal to 4. Because this is an exponential equation, we do not need to be concerned about extraneous solutions, but substitution will show us that when we have 3 times 4 minus 8, we do indeed get 2 to the 4th, which is equal to 16. In another example, we have 27x to the 3rd, or 27 to the x plus 3 power is equal to 9 to the x minus 1 power. Since both of these can be rewritten with base of 3, as seen here, we can rewrite this as 3 to the 3 times x plus 3, and 3 to the 2 times x minus 1. We'll thus set the exponents equal to each other and use the distributive property. Then, solving the resulting linear algebraic equation, we obtain x is equal to negative 11. Once again, this exponential expression, 27x plus 3, well, 27 to the negative 8 and 9 to the negative 12 are both permissible because we can have negative exponents. If we verify this using a calculator or simply by using the tool of writing it out manually, we can see that these two expressions are indeed equivalent. If it is not possible to have a common base, as in this example, 40 times e to the 0.6x minus 3 is equal to 237. 237 is definitely not e raised to some power, even if we divide both sides by 40. So what we're going to do here is we're going to note that this has a base of e. So I'm going to take the natural log of both sides. Now, because this is the natural log of e to the 0.6x, that will give me that 0.6 times x is equal to the natural log of 6. Therefore, I can divide both sides by 0.6, and I can get x equals the natural log of 6. Substitution will show me that this does in fact work. An approximation of this value would be approximately 2.986. Just keep in mind that if you substitute that value, you're going to get something that is very close to, but not actually equal to, 237. Therefore, what I've done here is substitute natural log of 6 divided by 0.6, and by the laws of logarithms, I get e to the natural log of 6 is actually equal to 6, so 40 times 6 minus 3 is going to be equal to 237. So if I use that rounded value of 2.986, it will give me an approximation. It will be very close to 237, but it will not be exactly equal to it. Additional solving with logarithms can happen when we have two different bases, both raised to a power. Now, in the other example, 237, you could conceive of that as being raised to the power of 1. But here I have 5 and 4 for my bases. What I can do here is take the log of both sides. Now, I'm going to take the natural log. You can choose to take whatever log you like. I like the natural log because it does show up on every calculator. And I'm then going to apply the properties of logarithms. So I'll get x minus 2 quantity times natural log of 5 and 2x plus 3 times the natural log of 4. I'll use the distributive property here and expand that out. Then I'm going to gather all of my terms that have an x in them on the same side and all of my terms that do not have an x on the opposite side. My expression therefore will look like this, and I'm going to factor out that x so that I can solve for x. Here it is, x times the quantity natural log of 5 minus 2 times the natural log of 4. And I do leave this way. I don't write natural log of 4 to the second power or natural log of 16. I just think it's easier, and it is what you're going to see more frequently. So I will divide both sides by natural log of 5 minus 2 times the natural log of 4, and I get the expression shown here. Now this you can evaluate and come up with a decimal value. You also can substitute it into your expression to determine and to see that you can substitute this value of negative 6.34 into your original expression. So you would have 5 raised to the negative 6.34 minus 2, or 5 raised to the negative 8.34 power. And you could see if that is equal to 4 raised to the 2 times negative 6.34 plus 3 power. Again, just as previously, that is going to give you a solution that is approximate rather than exact. So you do just want to keep that in mind. Another problem that you're going to see with some level of frequency is exponential equations in quadratic form. Let's look at how these are in quadratic form. You can see that we have e to the 2x power minus 4 e to the x plus 3. So that's something that looks like u to the 2x minus 4u to the x plus 3 equals 0. So we can take this as our variable, and we're going to have u to the x and u to the x in our parentheses, and then we can factor. Please note that it's really important here to have this equal to 0. You may need to do some adjustment prior to doing any of that work. So we're going to factor that expression. I factored it just using u. I have u minus 3 and u minus 1 equals 0. I end up with e to the x power is equal to 3 and e to the x power is equal to 1. Now, fortunately, both of these cases, I'm going to be taking the natural log on both sides of a positively valued expression. Keep in mind that taking the natural log, or really any log, of a negative expression is going to produce extraneous solutions. You do want to be watchful for that when you're working in quadratic form, or indeed with any sort of exponential or logarithmic equations. So I have x is equal to the natural log of 3, or x is equal to 0. With x being equal to 0, we can solve that by inspection. It's pretty easy. X equals the natural log of 3. You will probably want to use your calculator to verify. Again, please note, in general, instructors are looking for these exact answers. If the problem wants a rounded answer, particularly in application problems, it should tell you the number of decimal places that you should be rounding to. Okay, so we also can be using properties of logarithms to solve equations. I have a couple of slides on this. Please remember that you can always condense and expand logarithms to make it easier for you to solve equations. So here you'll notice we have log to the base 2 of x plus log to the base 2 of x minus 7 is equal to 3. It's going to be easiest to solve this if we think about combining and condensing this logarithm. So I have log to the base 2 of x times the quantity x minus 7 is equal to 3. And because of the properties of logarithms, we know that 2 to the third power must be equal to x times the quantity x minus 7. So I'm going to rewrite this as what you see here, x squared minus 7x is equal to 8. This allows me to factor, and then I'm going to factor that expression and solve for x. Now this is going to yield two solutions, x is equal to -1 and x is equal to 8. In one of these cases, x -1 is going to yield a domain error when I verify. You can see right here and here as well. So that is not going to work. It is an extraneous solution. However, x equals 8 is going to work out just great. Therefore, the only answer here is x equals 8. Please be sure that you are writing both solutions and noting that x equals -1 is an extraneous solution. In another example, you can see we have natural logs all over the place. So I have this expression, and then I'm going to use the one-to-one property of logs. X plus 2 divided by 4x plus 3 is going to be equal to 1 over x. Now I'm going to rewrite this as x times the quantity x plus 2 is equal to 4x plus 3. And this gives me that x squared minus 2x plus 3 is equal to 0. I'll factor that, so my apologies, that should say x squared. And once again, we are going to end up with x equals -1. X equals -1 will again yield an extraneous solution. My other value here of x equals 3 will not yield an extraneous solution. It will turn out to be something that works just super. But -1, big frowny faces, that does yield a domain error. So once again, you do need to be careful when you are using properties of logarithms. You could end up with extraneous solutions going on. In this application problem, we have $20,000 invested at a 9.5% rate of return compounded monthly, and after how many years will it reach a value of $500,000? So because I see that this has been compounded monthly, it's really important to use the compound interest formula. I've written this down here. A is equal to P times the quantity 1 plus R over N times NT. Substituting in the values that we know, we have 500,000. That's the amount that we want to have. 20,000 is our initial principal. 0.095 is our rate of return, and the 12 represents compounding monthly. So we'll clean this up. And 500,000 divided by 20,000 is equal to 25. What's inside our parentheses is equal to 1.00796167. And I'm going to use that as the base of my logarithm. I will be using the change of base formula here, or you can use natural log on both sides, whatever is going to be easier for you to do. If you use the base of 1.00796167, you should be using the change base or a function on a graphing calculator to get that done more easily. So you can see that, again, this is what we would end up with the change of base formula. Natural log of 25 divided by natural log of 1.00796167 is equal to 12t. And t is going to be equal to approximately 34 years. So that means that if you invest $20,000 at the age of 20 and you find yourself with a 9.5% rate of return compounded monthly, then by the time you're in your mid-50s, you will have $500,000 even if you do not add on any money. So that's the power of compound interest that I've been talking about since the beginning of this chapter. And I hope that this slide deck has given you some ideas on how to effectively solve exponential and logarithmic equations. Thanks so much and have a great day.